This is a camera that I built last year that shoots at 1 billion frames per second. What could possibly be cooler than that? A camera that shoots at 2 billion frames per second in HD. This camera, consisting of 1 mirror, 1 lens, 2 tubes, cables, one of the weirdest camera flash bulbs probably ever built, and a few hundred lines of Python, is not only fast enough to watch light move, it's fast enough to see the past. Think about the weirdness that might cause during this first demo. After my video about the billion frame per second camera, there were so many suggestions in the comments for cool things to set up. And today in the garage, I have the most requested experiment. This is a high power laser that I have actually focused this time, and it shoots down to the other end of the garage where I have a mirror, where that beam bounces back into another parallel mirror. So this beam of light is going to ricochet back and forth until it finally misses a mirror and hits the wall down there. This is what that setup looks like with a long exposure photograph on a camera, very similar to what your human eye would see if you were standing here with me. And this is what that looks like at 2 billion frames per second. Light moves about 6 inches or 15 centimeters per frame of this video. This beam of light is traveling at the universe's speed limit. Light in any reference frame will never move any faster or any slower than this speed. But what happens if I move the camera? This clip looks dramatically different. The light traveling away from the camera appears much slower, and the light traveling back towards the camera looks dramatically faster, like almost instant. And that's like really weird, because I just finished saying that light always goes the same speed no matter what. So if you have an idea as to why the light in that clip looks so strange, leave it in the comments while the title card plays. Because in this video, I'm going to show you how I built the upgraded version of my ludicrously high-speed camera, and we're going to get to the bottom of this light speed mystery. Today I want to take a video of the light leaving this laser, traveling across this room. Through all of this, I was becoming increasingly frustrated that LiDAR works. Look at that! That is so fast! How to tastefully illuminate my entire garage with a single laser diode. Since then I've upgraded, and now I have this. I completely overhauled the motion stage and optics train in order to reliably record in HD. I got better at signal processing and all of the electronics necessary to move data really quickly between the sensor and the computer in order to not only reduce the noise, but also record at twice the frame rate. This is a side-by-side comparison of the disco ball shot from the first video. New one looks a lot better. In order to explain what was bad about the original camera and what's improved about this setup, I kind of need to explain how I'm able to record at 1 billion frames per second. Basically, if you want to record video at 1 billion frames per second, you pretty much can't. Not at any reasonable resolution, with any reasonably accessible consumer technology for any remotely reasonable price, which is why setups like this kind of cheat. A lot of the comments on the first video, I guess really on the short, that didn't have time to fully explain everything, thought that this was a stroboscopic technique, where it was like a time lapse. I was just taking discrete pictures and then putting them one after each other. But that's not how this setup works. This camera and the new camera over there are literally capable of recording a video at 1 billion frames per second, or 2 billion frames per second. The catch is that it's only a 1x1 pixel video. That's right, I can only record 1 pixel at a time. So when that laser turns on, this camera may record a video that looks like this. Very exciting. In order to build up a useful image, I have to point the camera in a bunch of different directions and record a bunch of separate 1 pixel videos. Every one of these videos is a video of a distinct event that did not happen at the exact same moment in time. But if all of these videos are synchronized and we take many 1 pixel videos, we can tile these videos next to each other and play them all back at the exact same moment and get something that looks like a video. That tiling process gives us a real accurate representation of what a true 2 billion frame per second camera would see if instead of recording the data 1 pixel at a time, we had like over 900,000 of these sensors all pointed in different directions from the camera, and we recorded a single shot event with all the data coming in at once. That's just a significantly more expensive way to do it, and it really wouldn't give us any better of a result. Since the light sensor I'm using is pretty sensitive, considering what we're asking it to do, and this whole printed assembly is pretty heavy, I basically just have my single pixel camera pointed at the ceiling, and then the view from that camera is guided around by this gimbal mounted mirror. Every unique direction that I can point this mirror in becomes its own pixel in the final image. So pointing precision and repeatability are like ludicrously important upgrades that differentiate this camera from that camera. The original camera had the mirror being direct driven in both axes by these sort of janky hobby servos, and the whole assembly was on this, wobbly 1/4-20 all-thread mount. It wobbled, it drifted, it would break if you looked at it funny. Now I want to keep improving this camera, especially the space. Oh God, did I just snap something? Oh. In the last video I asked for suggestions, and many of you recommended a specific type of servo with a built-in encoder. In order to get an HD picture, a minimum of 720 pixels tall by 1280 pixels across, I needed to have some pretty darn good angular resolution on my mirror. A 12-bit encoder breaks a 360-degree rotation up into 4,096 different directions. So by direct driving the yaw motor, I can get 1,280 different values by swinging the motor through a 112-degree arc. That's a pretty reasonable field of view, comparable to a regular camera with a wide-angle lens, like the one that you're viewing me on right now. So that works, but it just barely works. And for the pitch motor, it won't work. For the pitch motor that tilts the mirror up and down, I not only needed more stable pointing, but my angular resolution was cut in half. Think about a beam of light bouncing off a mirror. If I tilt that mirror by 5 degrees, the path light will take bouncing off that mirror changes by 10 degrees. It gets doubled because there's an angle on both sides of the mirror normal. To handle this, I thought about gears, I considered mechanical linkages, I thought about getting a higher resolution encoder on the motor, but eventually settled on timing belts and pulleys. I was initially worried that belts would stretch and wouldn't be accurate for exact pointing, but I actually found a paper where the researchers tested exactly this, the repeatability of angles achieved with a belt drive, and they said it was cool. Science is awesome. So now with the belt drive system, a large and easily controllable motion of the motor becomes a small and precise motion of the mirror. I collect data in horizontal lines, and while the mirror sweeps from side to side, the laser light is blinking on and off repeatedly. Using a regular high-speed camera and some split-screen cheating to film the home-built ludicrous speed camera, this is what that looks like. The mirror spins so slowly that each time the laser blinks on, the mirror is effectively stationary for the duration of the measurement. The light blinks on and off almost 3,000 times per second, but the laser is only on for about 15 nanoseconds at a time. This means the light is actually off for literally 99.99% of the time. And while it's on, it's about 7,000 times brighter than it appears to a regular camera I'm filming with now, or to the naked eye. Your eyes do an awful lot of averaging. This new motion stage required a lot of trial and error, mostly self-inflicted. My, let's call it frugality, decided that these tiny cheap plastic motors were probably okay to swing around this big heavy assembly with a large moment of inertia. Go. Jeez. God, that sounds awful. Turns out that when you get the whole swivel assembly swiveling, and then the motor tries to lay on the brakes, the big swivel assembly keeps on swiveling. Yeah, that's broken. And in this case, it shredded at least one of those little tiny plastic gears inside the servo. I shouldn't be able to pull teeth out of my motor. I believe the correct answer to this is actually a software fix to a hardware problem. Hey, look at that. And that's to just limit the acceleration of the motor. The guts of this servo actually can control limits for velocity, acceleration, and some PID tuning stuff on board, which is awesome, even if I'm really bad at PID tuning and am willing to accept some really annoying bouncing at the endpoints. And after figuring out which LLM code snippets were useful and which LLM code snippets were the reason I'd been frustrated for hours, I got the motor accelerating smoothly and decelerating smoothly, so in normal operation it would never strip itself out. Unfortunately, this is still a software fix to a hardware problem, and I was not happy with it. There were still so many ways for the system to crash and to trash another motor, so I wanted a torque limiter. But I couldn't find a torque limiter or even a torque gauge that went as low as the limits on this motor. So I built both. This has been bouncing around in my head for like the last day and a half. I think I've got an idea. This should be able to connect two shafts. It should be able to unstick smoothly and with a tunable amount of stress because the magnets are going to be far away. Using magnets instead of springs means that when it starts to spread apart, it'll spread apart much faster, whereas springs, get tighter as you retract them. This apparatus is made from 6 3D printed parts, 4 magnets, and some glue. Really, it could have been 2 3D printed parts, but I was paranoid about the layer lines getting stuck on each other sideways, so I printed the little teeth panel sideways, but the hub's flat, so the arms would be strong but flexible. It's a whole thing. Basically, if you ever try to turn this shaft too hard, the bottom teeth exert a force pushing the combs away from each other. Once this force becomes large enough to overcome the magnets holding them together, the whole thing slides out and is free to harmlessly spin. Now, with the torque limiters installed, even if this whole carriage crashes somehow, the torque limiter breaks free like a mechanical fuse and the motor doesn't get shredded. Okay, now it's mad. Oh boy. Now, all of that effort was just to point a mirror, but all of the light that bounces off this mirror eventually finds its way into the optics train. Actually, calling this an optics train is a little aggressive. It's one lens and one pinhole. I'm using a longer focal length lens than I did last time, but it's still just one lens. All the light that comes in from one direction then gets focused to a point by this lens. In the last video, I equated this pinhole to the aperture in a regular camera lens. But that's true, but it's really only true for the out-of-focus light. In this case, because I have the pinhole at the intended focal length of the lens, it would be more accurate to say that I'm using this pinhole to set the pixel size of my camera. I cut a variety of pinhole sizes on the big laser, and they were mostly round. Yeah, I haven't actually fixed this yet, so... And although I cut out a whole bunch of different pinhole sizes and calculated that a 1mm pinhole would be correct for the amount of angular resolution that I'm trying to achieve, I ended up going with the bigger 2mm one because I'm a glutton for data, and I was willing to accept slightly fuzzier images as long as I could cram 4 times as many photons through that hole. The fun part is that this lens is actually attached to this big 3D printed column. You can open it up to look at the focal plane, you can spin the mirror up and down on this big long thread in order to focus the entire system. It's great. To get the optics all trained in, you shine a bright light at the scene, open the doors, and set a white piece of paper down in place of the pinhole. The light coming in off the mirror gets focused down to a nice little image on the paper if you get the height of the lens just right, and then we can lock the lens in place with this ring. Since we want to create as sharp an image as possible, we want each pixel to be formed from the light that only comes from one direction. So we don't want to sample the light from this entire image, just a tiny piece of it. That's what this pinhole is really doing. It's selecting part of this image to analyze in each measurement and blocking most of the light with black cardboard. Now the light that does pass all the way through the pinhole in the middle makes it down to the sensor. Okay, chapter 2 was pretty short, but the electronics are the complicated part, so we're moving on. I'm using the same photomultiplier tube as last time for my light sensor. PMTs are awesome. They are so ludicrously sensitive that they can detect single photon events, and vacuum tubes are just gorgeous. So when I started adding electronics to this project, I actually spent a couple days thinking that my PMT was broken, and I literally had the page open to order a new one. So last night I spent like 2 hours fighting with the photomultiplier tube. And I could not figure out what was wrong. I had like a ludicrous amount of noise, signal was terrible. All I wanted to do was see a single photon show up in the oscilloscope. I now have a single photon showing up in the oscilloscope. I forgot just how sensitive these things are. Even though the entire thing is closed off inside of opaque black plastic, these monitors are black, but they're on. And that's totally swamping it out. There's a reason that last year I went through the garage and covered every window, every light, every little indicator LED, and I could only run experiments at night. Once you get rid of the vast majority of the light though, you can get back to the world of detecting individual photons. But for now, just know that as light hits the sensor, the intensity of that light is converted to current in a wire. Current that can be converted to a measurable voltage with a 50 ohm resistor and fed straight into this oscilloscope. Oscilloscopes are really cool tools. This is actually a brand new oscilloscope, almost brand new after it tried to cook itself. And if we plug some wires into this marvelous contraption, it can tell us the electrical potential difference between this probe and this clip at a rate of 2 billion times per second. This is the instrument that's literally collecting and saving the data for this camera. Imagine we have some time-varying signal passing into the scope on these wires. Every half a nanosecond, the oscilloscope looks at the signal, measures it, and records a number digitally in RAM. It's doing this all the time, continuously saving data. But if it receives a specific signal, like a particularly strong or a particularly sharp signal, then it stops recording, takes the saved data, and plots it to the screen as a value of voltage over time, or in our case, with data from this sensor, light intensity over time. One really wacky thing I want to point out is how long it takes for information to pass through this system. I'm going to animate over this and I'm going to try to keep all the speeds exact, assuming that all the signals are perfectly sharp, which they're not, but bear with me. Imagine that we have a photon that has left the laser and it's traveling out into the middle of the room at about 1 foot every nanosecond. That photon is going to scatter off the droplet of fog that's suspended in the air, and it might redirect itself towards the mirror over here. So it's going to travel over, also at about 1 foot per nanosecond, until it hits this mirror, which is going to tilt it down, and it's going to pass through this lens. At that point, it's inside the camera, and the lens to the sensor is almost 60 millimeters, which means that it's going to take time for that light after it has entered the camera to reach the sensor. 4 frames of video worth of time just to move through the camera at the speed of light. Once that light reaches the sensor down here, it impacts a piece of metal which releases a single electron into the vacuum tube. That electron gets bounced around between a whole bunch of differently charged pieces of metal, releasing a whole bunch more electrons, turning our single event, our instantaneous photon being absorbed event, into a packet of like 1 million electrons that all get dumped into the wire at the same time. That whole process inside the vacuum tube took about 22 nanoseconds, and in the end, that process just dumped a whole bunch of excess electrons into this wire. Now, since this wire already has electrons in it, and we've like crammed a whole bunch more in one end, basically what happens is that everybody has to take a step forward. All the electrons in this wire start moving. And the useful information, that signal, the rate at which all the electrons start to take a step forward, is slightly slower than the speed of light. I haven't actually measured the velocity factor in this cable, but let's assume it's like 5 or 6 nanoseconds. At this point, I don't actually know what the delay is, but somehow inside that scope, it's measuring the voltage on this wire, basically the local scrunchedness of electrons. If there's a lot of electrons scrunched together, it's going to record a large negative peak in voltage that we interpret as light. And that happens 2 billion times per second. And that data is being stored digitally, and then it can be transmitted to the computer. If we just zoom out and look at this process, it is absurd to think about. If we're recording a video with this camera, and we just saw recorded the fact that the laser turned on, and we call that frame 0, the light entering the camera lens at that moment contains information about frame number 58. Information about 57 frames of video are moving through this camera at once. Totally analog. By the time we've recorded this frame, information about this frame is here, and at the wall, the scene might look more like this. It's like we're perceiving the world on a delay. It's insane to think about. Like if you froze time and looked at this wire, you'd see scrunching of electrons and say, ah, those are different frames of video at the speed of electricity. Absolutely wild. To make sure that all the photon data we record plays back properly, that all of our 1x1 pixel videos start at the same instant and we don't get something like this where half the frame is on a delay, we need an additional synchronization or triggering signal that can be measured by the oscilloscope to give us a timestamp. Something to register all of the data we collect back to the moment that the laser turned on. The last key leap of electronics that allows this system to achieve 2 billion frames per second without a truly unreasonably expensive oscilloscope is that I am both triggering the scope and collecting data on the same channel. Electrical engineers in the audience may want to avert their eyes at this time. This scope can only hit 2 gigasamples per second if I use a single channel. I did not realize that when I bought this scope. So I'm not just feeding the PMT signal in and then terminating it with a 50 ohm resistor. I'm actually terminating that signal with another 50 ohm cable pointed all the way over there towards the laser. This means that information from the PMT is actually traveling down this cable sort of past the scope and just straight on into this cable. And as the information scoots on by, the scope just kind of looks at it. At the same time, every time that laser blinks, there's a current being fed through the laser feedback signal that comes down one of these wires and gets sent onto the second board. You can see I planned really well, where that signal gets inverted, amplified, and sent down here into a significant quantity of coax, and then that heads over to the oscilloscope. But that information is traveling in on this line. So we actually have data moving in 2 directions through this piece of coax. The, at that point, useless PMT data that's just getting shot into hundreds of feet of cable, and the synchronization data. The result of all of that is a graph that looks like this, where you get all the PMT information about the brightness of the light, then sometime later, a pulse that can be used to line up all the videos after the fact, with an added bonus that the synchronization signal can't add noise during the critical measurement because it's literally too far away in time. This was not easy to figure out, and at least once I had a literal shower thought that became a bizarre Terminator setup. But in the end, the answer was to invert the timing signal so it had opposite polarity to the PMT signal, and unfortunately eat some attenuation by terminating both ends of the line with 50 ohm resistors, but nothing at the scope. In order to make these signals reach the scope at different times, you could design a really complicated delay circuit to get exactly the time offset you wanted, or you could just buy another 500 nanoseconds of cable. I didn't even bother to unspool it. If this cable section sounded like complete soup to you, don't worry. I've got a video about impedance matching that actually got relegated to the second channel because it was a little more technical than the electricity waves video that was on this channel, but you should go check that out because I think it's really fun. And in making that video, I learned what I needed to know to make this project possible. There is no way that any of this would have come together without me learning by making that whole series about electricity that I started a couple of years ago. Really slow out there. Wow. And on the way back, it's like 1, 2, 3. Wow. Oh, that's perfect. I love it when the data shows you exactly what you want to see. Doesn't always happen. At the beginning of this video, I said that that camera could see the past. And to be fair, every camera can see the past. Your eye only ever sees the past. The screen that you're watching this video on right now lit up, and it took a few nanoseconds for that light to reach your eyes before your eyes had any chance to perceive that that light existed. But in the vast majority of cases, this just doesn't matter. My camera can take at minimum 1/4000th of a second exposure. That means that it is not only looking at light that is immediately in front of the camera, it also can look at light from 50 miles away within the same exposure. So regular cameras don't ever have to deal with the propagation of light because they just do too much averaging. For all the ridiculousness of the path that the information takes through this camera, by the time the information is in the camera, it's all taking the same path, so it kind of doesn't matter. This is not true, however, for information traveling outside the camera. This camera can perceive the motion of light because light traveling this path gets to the camera faster than light traveling this path. In the first case, light may take 5 nanoseconds to get to a droplet of fog in the air, and then maybe 15 nanoseconds to bounce all the way over to the camera. And in the second case, maybe 15 nanoseconds before it has hit some fog, then 15 nanoseconds to get to the camera. This extra path length is what the camera perceives as a delay. And it only works perfectly because the path back to the camera is the same length in both cases. The camera is seeing the light at this location and the light at this location both 15 nanoseconds in the past. If you look at this video and think, wow, the light at the beginning seems to be a tiny bit faster, then you are really observant. It's slight. But with this camera, the path light takes to get to the camera is critically important. When we point the camera in different directions, what we're really probing is this set of path lengths. And this distance to the camera is not the same as this distance to the camera. So things get weird. When we reposition the camera to be behind the laser, this effect is much more extreme. As the light reflects from farther and farther locations, it not only takes light longer to get to the place where it scatters, but it takes longer to get back to the camera. Because we're basically doubling the path length for the light, the speed of light appears to be almost half of its true value. If you want to think about this another way, from some sort of classical objective perspective, the camera sees things near it with very little delay, but sees distant objects farther and farther back in time. The image formed by this camera is not an objective view of the world at a single moment in time, but a perspective taking a slice obliquely through time. For the light bouncing back towards the camera, or equivalently if we put the camera at the far end of the garage, we have the opposite effect. If we look at the path lengths for each position in this case, the total path lengths are almost the same. As the scattering location gets farther from the light source, it also gets closer to the camera, so we really can't detect much of a difference in travel time. With both mirrors set up so the light can bounce back and forth many times, we get to see both the artificial slowdown effect and the artificial speed up effect in the same clip, and it looks pretty trippy. I also need to point out that this has nothing to do with the actual speed of light changing or being different in different directions. These artifacts are the unavoidable result of us sensing the world around us using our eyeballs by absorbing radiation that has a finite speed. We will never know exactly what the world looks like everywhere at the same instant in time. In fact, that whole question is sort of assuming that the same instant in time exists everywhere in the world, and that doesn't even work. You can also see this in the disco ball footage. The light rays traveling towards the camera through the fog from the disco ball show up almost instantly, and all the spots of light where those rays actually intersect the wall behind the disco ball show up after a significant delay. That's because the wall behind the disco ball is farther from the camera, so we're seeing it farther in the past. I love this conclusion as a really weird quirk of ultra high speed filming. And a similar technique where the light travel time to the observer was a critical parameter was actually first used to measure the speed of light by Ole Romer in the 1670s. But that was at the scale of like planetary orbits, and this is at the scale of stuff in a garage. It feels a lot more real to see these effects play out with like human scale objects. And now that I've got this camera running, I'm planning on making a whole bunch more videos with it. So subscribe if you think that sounds interesting, and thanks for watching. I'll see you next time.